The steel groans at 3:47 in the morning. Not the creak of age, but something deeper. A resonance that traveled through 18-inch tubes packed with chromium alloy that shouldn't have worked, through wrought iron rivets hammered by men who couldn't surface too quickly or they'd die. Below the roadway deck, in the service tunnel that runs the length of the span, maintenance logs record the temperature at 40 to 1 degrees. The river is 78 feet down. The bedrock is 78 feet below that. Between them, silt, sand, pressure, and the bodies of at least 15 men whose names appear in a physician's report from 1871 but nowhere else. This is the Eads Bridge, and it was never supposed to need maintenance, because James Buchanan Eads said it would stand as long as the pyramids. 20 years after it opened, a tornado drove a 2x10 plank through 5/16-inch iron and scattered chunks of the eastern approach across a football field. It stood anyway. Here is the question. When a structure outlasts its purpose, its builders, its justification, and the industry it was designed to save, does it serve the city, or does the city serve it? The East Pier went down first. October 1869. The caisson, a wooden box the size of a small warehouse, sealed at the top, open at the bottom, floated into position above the sandbar where steamboats had been running aground since anyone could remember. Inside the box, 2 steam engines on the surface, pumping compressed air into a chamber 100 feet below. Inside the chamber, 40 men with shovels. They called it going down. You entered through an airlock, a cylindrical shaft with 2 doors that couldn't open at the same time. The first door closed behind you. Air hissed in until the pressure equalized. Your ears popped. Some men's eardrums burst on the first descent. The second door opened, and you climbed down a spiral staircase lit by candles that burned differently under pressure, the flames shorter, bluer, consuming oxygen that cost money to pump. At the bottom, the work was simple. Shovel mud and sand into a tube. A pump on the surface sucked it out. The caisson sank an inch, 2 inches, a foot. Stonemasons on top added another course of limestone. The structure grew downward and upward simultaneously, pursuing bedrock that the engineers said was at 60 feet but turned out to be at 78. The air pressure increased with every foot of descent. At 30 feet down, the pressure inside the chamber was 13 pounds per square inch above atmospheric. At 60 feet, it was 26. At 78 feet, the final depth, it was 34 pounds per square inch. Roughly twice the pressure of a car tire today, except the tire doesn't contain men who need to breathe. James Moran was Irish. 32 years old. Worked the East Pier. On March 19, 1870, he finished his shift and came up. The usual procedure: climb the spiral staircase, wait in the airlock while pressure normalized, emerge into daylight. He made it to the surface. He made it to the boarding house. He was dead by morning. The post-mortem examination, one of the first conducted on a caisson worker, found gas bubbles in his blood vessels, particularly around his brain and heart. The attending physician, Dr. Alphonse Jaminet, had no framework for understanding what he was seeing. He knew the phenomenon was related to pressure change. He knew it was happening more frequently as the caisson sank deeper. He knew the symptoms: joint pain so severe men bent double, hence the bends; paralysis; blindness; convulsions; death. What he didn't know was why. Nitrogen absorption in tissue under pressure, released too quickly on ascent. The science wouldn't be properly understood for another 30 years. But men were dying now, in 1870, in the service of building something unprecedented. Jaminet set up a floating hospital next to the pier. He documented 119 cases of decompression sickness during the bridge's construction. 15 men died. 2 were permanently paralyzed. 77 suffered severe symptoms and survived. His recommendations: slower decompression, shorter shifts, rest periods between descents. The recommendations were partially implemented. The work continued. The bridge company paid wages. It didn't pay medical bills. There was no workers' compensation in 1870. If you were injured, you lost your wage. If you died, your family received nothing unless they could prove negligence, which required a lawyer, which required money. James Moran's widow did not sue. The workers who went down kept going down, some because they needed the money. Caisson work paid better than surface work, precisely because it was dangerous. Some because they'd already invested weeks acclimating to the pressure and didn't want to start over somewhere else. Some because they believed Eads when he said the bridge would be the greatest engineering achievement of the century, and they wanted to be part of it. By February 1871, 4 limestone piers rose from the river bottom. Each pier, 48 feet wide, 106 feet tall from bedrock to the point where the steel arches would begin. Each pier, solid masonry, built on pneumatic caissons that cost 120 workers their health or their lives. The bridge company's financial reports for 1877 listed caisson construction costs at $1.2 million. This figure included timber for the caissons, limestone blocks, cement, wages for masons and engineers. It did not include the floating hospital, Dr. Jaminet's salary, burial costs, or the economic value of 15 men who would have worked for another 30 or 40 years. From the Illinois shore you could stand and watch the piers grow, limestone blocks swinging from cranes, steam engines chugging, men emerging from the airlocks bent over, some carried on stretchers. One newspaper reporter noted that the workers' faces looked gray when they came up, as if they'd been underground for days instead of hours, which in a sense they had been. The piers were complete. The killing was over, at least the killing by pressure. Now came the question of what to build on top of them. A bridge made of steel, a material that had never been used at this scale, designed by a man who had never built a bridge, spanning a river that everyone said couldn't be spanned at this location. The bedrock was there. The piers were there. The bodies were down there, or in cemeteries across St. Louis, or disabled and working whatever jobs would take a man who couldn't stand up straight anymore. And the bridge was about to become famous for something other than the men who died building it. Andrew Carnegie did not want to sell steel to James Eads. This was 1872. Carnegie was 36 years old, vice president of Keystone Bridge Company, and already wealthy from railroad investments. Keystone had won the contract to erect the bridge's superstructure. Carnegie would provide the steel through his supplier Butcher Steel Works of Philadelphia. The problem was Eads' specifications. He wanted steel of uniform quality, tested to standards that didn't exist yet. Each component had to meet precise tensile strength requirements. Any piece that failed inspection would be rejected and re-rolled. Carnegie wrote to a colleague, "Of all men, your man of real decided genius is the most difficult to deal with practically." Steel in 1871 was not what steel is today. The Bessemer process, invented in 1854, allowed mass production of steel by blowing air through molten iron to remove impurities. The Siemens-Martin process, developed in the 1860s, used regenerative heating to achieve similar results. Both processes produced steel stronger than wrought iron but inconsistent in quality. 2 ingots from the same batch might have different structural properties. Eads specified chrome steel for the bridge's tubular members. This was experimental. Chrome steel had been used in small applications but never in a structure of this magnitude. Carnegie argued for wrought iron, which was proven. Eads refused. Carnegie argued that the specifications were impossible to meet. Eads sent samples back for re-rolling. The contract specified that Keystone would provide all metalwork for the bridge, steel for the arches, wrought iron for the skewbacks, and some connectors, hardware for assembly. The price was negotiated before anyone understood how difficult it would be to meet Eads' standards. Butcher Steel Works produced test pieces for 6 months. They failed. The superintendent complained that Eads was demanding perfection in a material that couldn't be perfected. Butcher withdrew from the contract. Keystone scrambled. Carnegie arranged for Chrome Steel Works of New York to take over production at a higher price. This triggered a minor financial crisis. The bridge company was already hemorrhaging money from construction delays and cost overruns. Carnegie's company wanted payment guarantees. Eads needed the steel, or the entire project would stall. The resolution involved J.P. Morgan. Morgan's banking house agreed to underwrite bonds for the bridge company, providing liquidity to keep steel production moving. In exchange, Morgan received equity and a seat on the board. This was how infrastructure worked in the Gilded Age: private capital, public benefit, concentrated ownership. Steel arrived in St. Louis in pieces. Tubular sections 18 inches in diameter, 12 feet long, threaded at the ends so they could screw together. Each tube was hollow, which reduced weight while maintaining strength. Each tube had to fit precisely with its neighbors, or the arch wouldn't close. There were no computer models, no finite element analysis. Eads calculated everything by hand, verified by Washington University mathematician William Chauvenet. The design called for 3 arches spanning the river, 2 side arches of 502 feet each, 1 center arch of 520 feet. At the time of construction, this would be the longest rigid span ever built. The arches would be supported during construction by a cantilever system, wooden towers on each pier, cables running over pulleys, counterweights holding the incomplete arches in place while workers added sections. Construction of the first arch began in spring 1872. Workers assembled the steel tubes on the piers, then extended outward over the water. No false work below, the river needed to remain open for steamboat traffic. Everything hung from the cantilever cables. Each new section added weight, increased tension in the cables, required recalculation of counterweights. Henry Flad supervised the arch construction. Flad was Eads' first assistant, a German-trained engineer who understood the mathematics of stress and compression better than most men in America. He worked from dawn until dark, checking measurements, adjusting cables, ensuring that the 2 sides of each arch grew toward each other at precisely the right rate and angle. The critical moment came in September 1873. The east and west sections of the center arch had been built out from their respective piers until only 5 inches separated them. This gap would be closed with a threaded iron plug. The plug had to be inserted when the temperature was exactly right, because steel expands and contracts with heat. Too cold and the gap would widen. Too warm and the sections would compress the plug and the arch might buckle. They waited for the correct conditions. Early morning, September 15th, temperature 47 degrees. Workers lifted the plug into position and began turning it. The threads engaged. The gap closed. The arch was complete, supported entirely by its own geometry. The cantilever cables could be removed, but they weren't removed immediately. Winter came. The cables contracted in the cold, pulling the arch upward and backward. The distortion was slight, a matter of inches, but visible. Investors panicked. Eads examined the problem, calculated the cause, sent a telegram, loosened the cables. They did. The arch settled into its designed position. Eads addressed the investors, explaining what had happened and why it wasn't a structural failure. He spoke with complete confidence. This was his gift, the ability to understand physical forces intuitively and communicate that understanding to people who controlled money. The investors believed him because he had been right before, because he said failure was mathematically impossible, because they had no other choice. The second and third arches were completed by May 1872. Now came the roadway, the railway tracks, the final finishes. Carnegie's men worked slowly, negotiating for bonuses. There was a confrontation about payment. Carnegie briefly barricaded the bridge entrance to ensure Keystone received what it was owed. The details are lost, but the fact of it appears in company correspondence. Carnegie and Eads, the industrialist and the engineer, fighting over money while the bridge stood nearly finished behind them. The final cost was calculated at $6,536,720.99. Some sources say $10 million. The discrepancy depends on whether you count land acquisition, legal fees, interest on bonds, and the cost of the tunnel connecting the bridge to Union Station. The Illinois and St. Louis Bridge Company had borrowed heavily. It would not survive to see the bridge's first anniversary, but the bridge was done. Tested with 14 locomotives. Tested with an elephant because popular superstition held that elephants wouldn't cross unstable structures. Dedicated by President Grant on July 4, 1870, the largest steel structure in the world, built by a man who'd never built a bridge before, using a material that most engineers considered experimental. It stood. That was the marvel. Not that it was beautiful, though it was. Not that it united the city, though that was the intent. But that it existed at all, that the calculations proved correct, that steel could bear such weight across such distance. 7 years of construction. $10 million in contemporary money. 15 men dead. 1 bridge. The bridge opened on July 4, 1874. By April 1875, the Illinois and St. Louis Bridge Company was bankrupt. This was not supposed to happen. The business model was straightforward: charge tolls for railroad traffic, wagon traffic, and pedestrian crossings. The railroad companies had agreed to use the bridge. The city needed the crossing. Revenue would cover debt service, operating costs, and eventually generate profit for investors. The prospectus Eads, circulated in 1867, promised returns of 400%. The prospectus was optimistic. Railroad companies had agreed in principle to use the bridge, but agreements made 7 years before completion don't account for changed circumstances. By 1874, Chicago had solidified its position as the Midwest's railroad hub. 6 bridges crossed the Mississippi north of St. Louis. Freight routing patterns had already shifted. The Eads Bridge was magnificent, but it was also late. The tunnel was the second problem. To connect the bridge to the Missouri Pacific Railroad and other western lines, Eads designed a tunnel through the limestone bluffs west of the river. The tunnel would run 4,000 feet, 30 feet below street level, emerging at Mill Creek Valley where the rail yards were located. This was necessary because the bridge terminated at the base of the hills and there was no other way to reach downtown. The tunnel contract went to William Skrenka and Company in 1872. Construction began in October. It was cut-and-cover work: dig a trench, build the tunnel, fill over it, restore the street. Simple in theory. In practice, cave-ins, groundwater, disputes with property owners whose buildings sat above the excavation. Skrenka's company decided the work was too difficult. They completed the section south of Market Street and withdrew. The section north of Market went to James Andrews, the stonemason who'd overseen pier construction. The tunnel opened with the bridge in July 1874, but it had problems. Ventilation was inadequate for locomotive smoke. The smoke-consuming engines that Baldwin Locomotive Works had supposedly designed weren't ready. Trains could cross the bridge, but the experience was unpleasant for passengers and dangerous for crews. Some railroad companies chose to avoid it. The third problem was the approach on the Illinois side. The bridge ended in East St. Louis, in the low Mississippi Valley, miles from the actual rail yards and industrial districts the Eastern Railroad served. Connecting tracks had to be built. Terminal facilities had to be constructed. This required cooperation from multiple railroad companies, each with different track gauges, different corporate interests, different opinions about who should pay for what. Coordination failed. Some railroads built their own connecting tracks. Others didn't. The result was a patchwork of access that made the bridge useful for some traffic and useless for other traffic. Freight that could have crossed the bridge went by ferry instead, because the ferry company, Wiggins Ferry, had better terminal connections and charged lower rates. The bridge toll was 5 cents per 100 pounds of freight. Wiggins Ferry charged 9 cents initially, then dropped to 5 cents to match, then offered a barrel of whiskey to regular customers. The ferry won most of the freight business. The bridge carried passengers and lighter traffic, but not the heavy railroad commerce that was supposed to generate revenue. Operating costs were higher than projected. The bridge required constant maintenance. Tightening bolts, repainting steel, inspecting for corrosion. The tunnel required ventilation, lighting, drainage pumps. Guardrails needed replacement. The approaches needed upkeep, personnel costs, toll collectors, maintenance crews, administrative staff. Insurance was expensive because insurers didn't trust steel bridges yet. Debt service was crushing. The bridge company had issued bonds at various interest rates to various buyers at various points during construction. Some bonds were secured by the bridge itself. Some were secured by anticipated revenue. Some were unsecured, sold to desperate investors near the end when money ran out. Total debt exceeded $7 million. Interest alone required roughly $500,000 per year. Revenue in the first 9 months, insufficient. The bridge company's financial statements for 1874 show tolls collected, operating expenses paid, debt service unpaid. By spring 1875, bondholders were demanding payment or foreclosure. The company had no money. Eads, who held significant equity, had no money to inject. The banks that had financed construction wanted their exposure reduced, not increased. The company filed for bankruptcy protection in April 1875. The bridge was sold at public auction for $2 million to a newly incorporated entity, the St. Louis Bridge Company. This new company was controlled by creditors of the old company, the bondholders who'd lost money on the original investment and now bought the asset at a discount, hoping to make it profitable. Many people were indicted in the aftermath. The specifics are murky, but the charges involved financial irregularities, misrepresentation to investors, possibly outright fraud. Aj was not indicted. He had designed and built the bridge. He had promoted it, certainly, and benefited from stock ownership. But the financial structure, the bond sales, the bankruptcy, these were handled by other men. Ashraya's reputation survived intact. The St. Louis Bridge Company operated the bridge for 2 years, 1875 to 1877. They renegotiated some debts. They improved tunnel ventilation. They negotiated better terminal agreements with railroads. Revenue increased, but not enough. In 1877, the company was sold again, this time to interests controlled by Jay Gould. Gould was a railroad magnate, notorious for financial manipulation and monopolistic practices. He controlled the Missouri Pacific Railroad, among others. He saw the bridge not as a civic improvement but as a choke point, the only railroad crossing of the Mississippi at St. Louis. Whoever controlled the bridge could control traffic, set tolls, favor allied railroads, and exclude competitors. Gould established what was called an arbitrary, a monopoly toll structure. Railroads that wanted to use the bridge paid what Gould charged. The rates were not negotiable. The St. Louis Merchants Exchange, seeing this, launched plans in 1886 to build a second bridge, the Merchants Bridge, to break the monopoly. That bridge opened in 1890, went bankrupt in 1893, and was acquired by Jay Gould's successors. By 1889, Gould and allied railroad companies had consolidated control of the Eads Bridge, the Merchants Bridge, the tunnel, the Union Station, the Wiggins Ferry properties, and most of the terminal rail facilities on both sides of the river. They incorporated this system as the Terminal Railroad Association of St. Louis. The TRRA was effectively a legal monopoly, a single entity controlling all feasible methods of railroad access to the city. This arrangement lasted until 1912, when the U.S. Supreme Court ruled in U.S. v. Terminal Railroad Association that the monopoly violated antitrust law. The court ordered the TRRA to provide access to all railroads on equal terms. The TRRA complied, technically, while maintaining control of the infrastructure and the ability to set toll rates. The bridge, meanwhile, continued operating. It carried trains. It carried wagons, then automobiles. It generated revenue for whoever owned it. First the bankrupt company, then the creditors, then Gould, then the TRRA. But it never generated the returns the original investors expected. The 400% profit Eads promised in 1867 never materialized for anyone who bought in at the beginning. B. Gratz Brown, Missouri's governor during the bridge's planning phase, owned the granite quarry that supplied stone for the piers. He was not indicted either. The intersection of political power and economic interest was assumed, not questioned. The fact that the governor who helped secure federal financing for the bridge also profited from supplying materials to it was noted in newspapers but generated no scandal. What generated scandal was the failure. The magnificent bridge that was supposed to restore St. Louis to preeminence, that was supposed to compete with Chicago, that was supposed to justify 7 years of construction and 15 dead workers. That bridge opened to celebration and closed its first year in financial ruin. The engineering triumph was unquestionable. The business case was not. The steamboat industry tried to kill the bridge before it was built. They failed, but not for lack of effort. The Mississippi River at St. Louis was steamboat territory, had been since the 1820s. By the 1860s, hundreds of vessels worked the river, freight haulers, passenger boats, towboats, ferries. The Wiggins Ferry Company alone operated a fleet that moved everything from single passengers to entire railroad cars across the water. The river was a highway, and the steamboat operators controlled it. A bridge changed the equation. Any bridge would create a physical obstruction. A low bridge would prevent tall stacked steamboats from passing. A bridge with narrow spans would constrain navigation during high water. A bridge with piers in the river would create turbulence and collision hazards. The steamboat interests understood this. They also understood that if railroad traffic could cross the bridge instead of using ferries, ferry revenue would collapse. So they lobbied. Specifically, they lobbied the Illinois state legislature to impose restrictions on any bridge construction across the Mississippi at St. Louis. The restrictions were ostensibly about navigation safety. In practice, they were designed to make bridge construction impossible. The requirements: the bridge must allow spans and heights previously unheard of. Clearance under the arches must accommodate the tallest steamboats operating on the river, including theoretical future vessels with even taller stacks. Pier placement must not obstruct navigation channels. The bridge must not interfere with the river's natural flow patterns. And, crucially, the bridge design must be approved by steamboat interests before construction could begin. These requirements were passed into law. James Eads, when he learned of them, understood immediately what they meant. Build an impossible bridge, or build no bridge. He chose the former. The arch design was partly dictated by the steamboat restrictions. Arches could span longer distances with fewer piers than truss designs. Arches could be built high enough to satisfy clearance requirements. An arch bridge with 3 spans, 2 side arches and 1 center arch, could provide the necessary openings while minimizing pier placement in the navigation channel. But arches at this scale required steel. Iron wouldn't work. Wood was absurd. Steel was unproven, but theoretically possible. Eads specified steel, designed the arches, calculated the required height and span, and presented the plans. The steamboat interests, having demanded an impossible bridge, received exactly that, a design that met their requirements but seemed impossible to build. They objected anyway. Too high, they said, which was contradictory because they demanded maximum height. Too expensive, which wasn't their concern. Structurally unsound, which was speculation. The real objection, unstated but obvious, was that a successful bridge would end the steamboat monopoly on river crossing. The objections continued through construction. When the piers were being sunk, steamboat operators complained they interfered with traffic. When the arches were being assembled, they complained the cantilever rigging was a navigation hazard. When the spans were nearly complete in spring 1874, they petitioned the Army Corps of Engineers to halt construction and demand the arches be torn down because clearance was allegedly insufficient. The Corps of Engineers held jurisdiction over river improvements. The chief of the Corps was Andrew Atkinson Humphreys, who had extensive experience with the Mississippi and considerable respect for steamboat operators. He ordered an inspection. Eads provided exact measurements. Clearance at normal water level was 52 feet at the center arch. The tallest steamboat operating on the Mississippi required 48 feet. The math was unambiguous. Humphreys approved the bridge. The steamboat interests lost. Construction continued. On July 4, 1874, the bridge opened. Steamboats continued operating beneath it, as they had been promised they could. Ferry traffic continued, though railroad ferry crossings declined. The river didn't stop flowing because steel spanned it. But the river had the final word, eventually. The bridge was designed to withstand wind, ice, floods, the normal extremes of Mississippi River weather. It was not designed to withstand a tornado because no structure in 1874 was designed to withstand a tornado. The science didn't exist. The concept of tornado-proof construction was marketing, not engineering. Eads claimed the bridge would stand as long as the pyramids. He said no natural force could tear it down. He said this in speeches, in newspaper interviews, in correspondence with investors. The claim was repeated so often it became part of the bridge's mythology. The Great Eads Bridge. Eternal, indestructible, immune to nature. May 27, 1896, Wednesday afternoon. The weather was warm and humid, typical for late spring in St. Louis. By mid-afternoon, a storm system moved over Illinois and Missouri. Thick clouds, green-tinged. Barometric pressure dropped. At approximately 5:15 p.m., a tornado touched down 6 miles west of the Eads Bridge. The tornado was massive. Modern analysis suggests F4 intensity with winds between 168 and 199 miles per hour. It carved a path up to 3 miles wide through St. Louis, destroying 311 buildings completely and damaging 7,200 others. Churches collapsed. Factories disintegrated. The Liggett and Myers tobacco factory, under construction with 500 workers inside, came down. 13 workers died. It was considered miraculous that 487 survived. Lafayette Park, one of the city's fashionable squares, was reduced to a wasteland. Trees more than 50 years old were uprooted and thrown several blocks. Iron fences around the park were twisted into unrecognizable shapes. Residential neighborhoods, Compton Heights, Soulard, Mill Creek Valley, were demolished. Block after block of wooden houses simply ceased to exist. The tornado reached the Mississippi River at approximately 5:30 p.m. Steamboats moored in St. Louis Harbor were torn apart. 16 vessels were destroyed. Some were broken into pieces and scattered from the Missouri shore to the Illinois shore. Workers and passengers on those boats, many drowned, some blown into the river, some crushed by debris. The exact count is unknown because several houseboats with poverty-stricken families aboard simply disappeared into the water. Then the tornado hit the Eads Bridge, the tornado-proof bridge, the eternal bridge, the bridge that no natural force could tear down. The tornado was powerful enough to drive a 2-inch by 10-inch wooden plank through 5/16-inch wrought iron plate. This is documented. The plank, embedded in the bridge structure, was photographed and later displayed as evidence of the storm's intensity. The physics of it: wind speed sufficient to accelerate a piece of lumber to projectile velocity, impact force concentrated on a small cross-section iron plate that couldn't deform fast enough to dissipate the energy. The main arches held. The steel tubes, the Roman arch geometry, the overbuilt design, these withstood forces that Eads never calculated because he didn't know such forces existed. But the eastern approach, the part that extended from the arch to solid ground on the Illinois side, did not hold. Nearly 300 feet of the eastern approach was torn away. Pieces of the bridge weighing several tons were scattered up to 100 feet from their original positions. Stone blocks were hurled hundreds of feet. A wagon crossing the bridge at the time was dashed to pieces, along with its 2 occupants. The destruction was total for that section, not damaged, not partially destroyed, but completely removed. The tornado continued into East St. Louis, where it did its worst damage. Scarcely a building remained standing near the riverfront. Everything was swept away. 118 people died in Illinois, including 35 at the Vandalia Railroad freight yard. The total death toll, at least 255 people. Some sources say 306, depending on whether you count bodies never recovered from the river or identified from the rubble. The tornado was on the ground for 20 minutes. Damage in 1890, $6. 10 million. Adjusted for inflation to present day, approximately $3 billion, the Eads Bridge required repairs. The eastern approach had to be completely rebuilt. The work took months. During that time, all traffic used the Merchant's Bridge, or the ferry. The bridge Eads said would stand as long as the pyramids had lasted 20 to 2 years before nature proved him wrong. It stood afterward, though. The approach was rebuilt. Traffic resumed. The bridge continued operating because the core structure, the 3 steel arches, had survived. They survived because Eads overbuilt them, because he used more steel than strictly necessary, because he didn't trust his calculations enough to build to the minimum. The caution he claimed he didn't need turned out to be what saved the bridge. The river didn't care about the tornado. The river kept flowing. Steamboats kept running, fewer each year as railroads dominated freight. The bridge kept standing, carrying traffic, generating tolls, serving purposes that shifted as the city changed around it. Eternal wasn't accurate. Adaptable was closer to the truth. Jay Gould died in 1892. The Terminal Railroad Association he created outlasted him by decades. The system he built, owning every feasible river crossing, every tunnel, every terminal facility, functioned exactly as designed. Nothing moved through St. Louis without paying tribute. The legal structure was elegant. The Terminal Railroad Association of St. Louis, incorporated in 1889, was technically a joint venture among multiple railroad companies. The Missouri Pacific, the Wabash, the Cleveland, Cincinnati, Chicago, and St. Louis Railway, the Louisville, and Nashville, all were members. They pooled their terminal assets, contributed capital, and operated the system cooperatively. Cooperatively in this context meant they collectively controlled access. A railroad that wanted to use the Eads Bridge, the tunnel, or the Union Station had to negotiate with the TRAA. The TRRA set toll rates. The TRRA determined which trains got priority. The TRAA decided which companies could build connecting tracks and where those tracks could go. Non-member railroads paid higher tolls than member railroads. This was explicitly stated in the rate structure. A member railroad paid, for example, $3 per carload to cross the bridge. A non-member paid $5. The justification was that members had invested capital in the system and deserved preferential treatment. The effect was that railroads either joined the TRRA, ceding some autonomy and paying membership fees, or accepted disadvantageous toll rates. Some railroads chose the third option, avoid St. Louis entirely. Chicago already had better connections to the east. Kansas City was developing as a western hub. St. Louis, despite the bridge, despite the tunnel, despite all the infrastructure investment, was losing ground. The TRRA's monopoly pricing accelerated the decline it was supposed to prevent. The monopoly was visible in the physical landscape. On the Missouri side, the tunnel connected the bridge to the rail yards in Mill Creek Valley. The tunnel had 2 tracks. The TRRA controlled both. If you wanted to move freight from Illinois to Missouri by rail, you used the tunnel. There was no alternative. The topography, the limestone bluffs, made surface routes impractical. The TRRA knew this. The toll reflected it. On the Illinois side, the situation was more complex. East St. Primo. Lewis was flat river valley with multiple rail lines converging. The TRRA owned the Eads Bridge, the Merchants Bridge, terminal rail yards, switching facilities, and large portions of the Wiggins Ferry Company properties, including Bloody Island. This network of ownership meant that even if you could technically avoid one TRRA facility, you'd encounter another TRRA facility somewhere else in your route. The coal tariff was particularly instructive. Railroads moving coal from Illinois mines to Missouri markets paid a tariff to cross the river via TRRA bridges. The tariff was substantial enough that several companies decided it was cheaper to locate their facilities in Illinois rather than Missouri. Granite City, Illinois was founded in 1896 specifically to avoid the TRRA coal tariff. The city's steelmaking industry developed on the Illinois side because the economics of crossing the river were prohibitive. This was wealth extraction at infrastructure scale. The TRRA wasn't providing a service at market rates. It was charging what the market would bear because it controlled a choke point. The railroad companies that owned the TRAA profited twice, once from their own freight operations and again from tolls charged to competitors. The U.S. government noticed. Antitrust enforcement in the early 1900s focused on monopolies that restrained interstate commerce. The TRRA, which literally controlled the physical crossing point for interstate rail traffic at St. Louis, was an obvious target. The Department of Justice filed suit in 1906. The case, United States v. Terminal Railroad Association of St. Louis, went to the Supreme Court. The government argued that the TRAA was an illegal combination in restraint of trade. The TRA argued that it was simply a shared terminal facility, that its member railroads had legitimate business reasons to pool resources, and that non-member railroads could negotiate access on reasonable terms. The Supreme Court ruled against the TRA in 1912. The opinion, written by Justice Lurton, acknowledged that terminal facilities at river crossings might naturally tend toward monopoly because building duplicate bridges was economically impractical. However, the court held that when a group of competitors controlled an essential facility, they had a duty to provide access to all comers on equal, non-discriminatory terms. The remedy: the TRRA had to admit new members upon reasonable terms. It had to charge uniform toll rates that didn't discriminate between members and non-members. It had to provide switching and terminal services to all railroads equally. The court didn't order the TRA dissolved, but it stripped away the monopoly pricing power that made the TRA profitable. The TRARA complied. Technically, they admitted new members, they published uniform toll schedules, they provided services. But the economics of railroad terminal operations meant that whoever owned the physical infrastructure retained significant power. Toll rates, even if non-discriminatory, still generated revenue. Scheduling decisions, even if theoretically fair, could favor some carriers over others in practice. And the TRAA still owned the Eads Bridge. Owned it until 1989, when they traded it to the Bi-State Development Agency and the City of St. Louis in exchange for the MacArthur Bridge. The MacArthur Bridge, built in 1917, was designed specifically to break the TRRA's monopoly by providing an alternative river crossing. It didn't work. The TRRA eventually controlled that bridge too. But by 1988, railroad traffic patterns had changed enough that the exchange made financial sense. The Eads Bridge, at that point, was carrying Metrolink light rail and automobile traffic. The railroad deck had been converted. The tunnel was being adapted for light rail. The Terminal Railroad Association no longer needed the Eads Bridge for freight operations because most freight now crossed on the Merchants Bridge, which the TRAA still owned and operated. This was the final transformation. The bridge, built to carry railroads, controlled for decades by a railroad monopoly, ultimately transferred to public transit because its railroad function had become obsolete. The structure remained, the ownership changed, the purpose changed. The physics stayed the same: steel and stone holding weight over water. The monopoly's architecture wasn't just the legal structure of the TRA, it was the physical architecture of the bridges, the tunnel, the terminal yards. It was the geography that made one location for a river crossing more practical than another. It was the cost structure that made building duplicate infrastructure economically irrational. James Eads built a bridge to connect St. Louis to the east and restore the city's commercial prominence. Jay Gould turned that bridge into a toll booth. The Supreme Court ruled the toll booth illegal. The city eventually inherited the bridge from the monopoly, and the river kept flowing underneath. Indifferent to ownership, indifferent to antitrust law, indifferent to the economic geography that human institutions imposed on it. The TRRA still exists. Still operates terminal facilities in St. Louis. Still owns the Merchants Bridge, which underwent a $222 million rehabilitation in 2022. The company is now jointly owned by 5 Class I railroads: BNSF, Canadian National, CSX, Norfolk Southern, and Union Pacific. This is legal because they provide access on non-discriminatory terms as the Supreme Court required. Whether it's meaningful competition or simply a modernized version of the same monopoly structure depends on your definition of those terms. The infrastructure persists. The arrangements adapt. The river crossing remains essential, which means whoever controls the crossing retains power, regardless of what the law says about how that power must be exercised. The bridge requires 32,000 gallons of paint. This is a recent figure from the 2012 to 2016 rehabilitation. 32,000 gallons to coat the steel superstructure with rust-inhibiting finish. The old paint had to be removed first. 9 coats accumulated over 138 years. Sandblasting, containment systems to prevent contaminated debris from falling into the river, environmental compliance for lead paint removal. The paint removal alone took months. 1.2 million pounds of steel was replaced. Not repaired, replaced. Struts, bracing, support members dating from the 1880s. Some pieces had been fabricated by hand, unique components that had to be precisely measured, then replicated using modern techniques. Other pieces were standardized sections that could be manufactured, but the specifications had changed. Steel composition in 2012 is not identical to steel composition in 1874. The workers encountered unknowns. This is the technical term in the project documentation. Unknowns. Elements of the bridge that didn't appear in the original drawings, modifications made during construction or in subsequent decades, repairs that left no records. A rehabilitation project on a 140-year-old structure becomes partly archaeological. You discover what you're working with as you work. The Metrolink track system was completely rebuilt: rails, ties, overhead conductor wiring. The bridge carries approximately 300 Metrolink trains per day, crossing between Missouri and Illinois. During rehabilitation, all trains shared one track while the other track was reconstructed. Then they switched. Total service disruption was minimized, but the logistical complexity of maintaining transit service while sandblasting and repainting the structure underneath the trains was substantial. Cost, $48 million total. $27 million from the American Recovery and Reinvestment Act of '09. Federal stimulus money earmarked for shovel-ready infrastructure projects. the remainder from federal transit grants and local matching funds. The project was initially estimated at $24 million. Bids came in at $33 to $45 million. Metro rebid the project. Bids came in higher, $36 to $49 million. This is normal for historic structure rehabilitation. Uncertainty adds cost. Regulatory compliance adds cost. Working around operating transit service adds cost. The alternative, building a new bridge, would cost an estimated $250 million. So $48 million to extend the life of the existing bridge by 50 to 75 years is economically rational, even if it's more expensive than originally projected. The project was delayed. Originally scheduled to begin in 2009, actual construction didn't start until 2012. Labor disputes between contractors and unions, disagreements about bid specifications, Federal Transit Administration concerns about schedule slippage, a pointed letter from the FTA in September 2011. Stimulus funds that aren't spent by September 2015 would have to be returned to the Treasury. The work was completed in October 2016. The bridge is now expected to remain functional until at least 290 to 1. This assumes continued maintenance, periodic inspections, corrosion monitoring, paint touch-ups, component replacements. The assumption is that someone will fund this maintenance, that the political and fiscal structures necessary to allocate millions of dollars for preserving a bridge will continue to exist. There is no guarantee of this. The bridge's history includes bankruptcy, corporate takeover, monopoly control, antitrust litigation, ownership transfer, and now public-private operation. Each transition involved uncertainty about who would maintain the structure and how it would be funded. The bridge has survived because at each transition, some entity with financial resources and operational responsibility took ownership. The current arrangement, Bi-State Development Agency/Metro, owns the superstructure and the lower deck. The City of St. Martin, Louis, owns the upper deck. This split ownership reflects the bridge's dual function, light rail and automobile traffic. Coordination between the two owners is required for any major work. The 2012 to 2016 rehabilitation involved both entities, multiple contractors, federal oversight, and coordination with the Terminal Railroad Association, which owns adjacent rail facilities. The bridge generates no revenue from tolls. Tolls were eliminated decades ago for automobile traffic. Metrolink fares are collected by Metro but go into the general transit operating budget, not specifically to bridge maintenance. The bridge is maintained because it's essential infrastructure, not because it's a profit center. This is a different economic model than the one James Eads envisioned or the one Jay Gould exploited. Maintenance costs are invisible until deferred maintenance creates a crisis. The 2012 rehabilitation was necessary because decades of minimal investment had allowed corrosion to progress, paint to deteriorate, structural elements to weaken. If the work had been deferred another 10 years, the cost would have been higher. If deferred 20 years, replacing the bridge might have been the only option. This is the maintenance imperative. A structure of this scale requires ongoing investment whether it generates revenue or not, whether it's politically convenient or not, whether the public understands the necessity or not. The bridge cannot maintain itself. Left unattended, steel corrodes, paint fails. Connections loosen. Eventually, structural integrity degrades below safe operating thresholds. The original construction killed 15 men. The ongoing maintenance employs hundreds: engineers, inspectors, painters, fabricators, construction workers. The deaths were concentrated and visible. The employment is distributed and routine. Both are costs of the bridge's existence, but only one appears in historical narratives. The Eads Bridge is unusual in having survived 150 years of continuous use. Most 19th century bridges were replaced decades ago. The Brooklyn Bridge survives, massively modified. The Eads Bridge survives, massively modified. What makes survival possible is not the original engineering, though that was exceptional, but the continuous decision to invest in preservation. This decision is not automatic. Other cities have demolished historic bridges because maintenance costs exceeded available funding. Other cities have allowed bridges to deteriorate until emergency closures forced reconstruction. St. Louis has chosen, repeatedly, to maintain the Eads Bridge. This choice reflects the bridge's symbolic importance as much as its functional utility. The bridge is a National Historic Landmark, designated in 1964. This designation provides some federal funding opportunities and imposes some preservation requirements, but it doesn't guarantee maintenance funding. Historic designation means you can't demolish the structure without extensive review. It doesn't mean anyone will pay to preserve it. The symbolism operates at multiple levels. For St. Louis, the bridge represents engineering achievement and civic ambition from an era when the city was more economically prominent. For transportation planners, the bridge represents infrastructure adaptability, originally built for railroads and wagons, now carrying light rail and automobiles. For engineers, the bridge represents a successful application of then experimental steel construction techniques. None of these symbolic functions pays for sandblasting or steel replacement. The symbolism creates political will to seek funding, but the funding requires federal grants, local tax revenue, and institutional capacity to manage complex construction projects on historic structures while maintaining transit operations. The $48 million rehabilitation purchased 50 to 75 years of continued operation. At the end of that period, another rehabilitation will be necessary. The cost will be higher. Construction costs increase. Environmental regulations become more stringent. The structure will be older and potentially more complicated to preserve. Someone in 2070 or 2090 will face the decision: invest in maintenance again or replace the bridge. The decision will be economic, political, and symbolic. The economics might favor replacement if construction techniques have advanced sufficiently. The politics will depend on who controls funding and whether historic preservation has political constituency. The symbolism will matter only if people in 2070 care about a bridge built in 1874. James Eads said the bridge would stand as long as the pyramids. The pyramids stand because they don't require maintenance. They're solid stones, slowly eroding, serving no function except as monuments. The Eads Bridge stands because people keep maintaining it. The difference is significant. Their names exist in fragments. James Moran, the first documented death, March 19, 1870. Born in Ireland, age 32. Worked the East Pier. Died of decompression sickness approximately 12 hours after surfacing. His widow's name does not appear in any record. John Myers, age 28, died April 18, 1870. German immigrant. Worked the West Pier caisson. Symptoms began during ascent: severe joint pain, difficulty breathing. He was carried to the floating hospital Dr. Jaminet had established beside the construction site. Jaminet's notes describe paralysis affecting Myers' lower body, then respiratory failure. Death occurred within 6 hours of leaving the caisson. Thomas Riley, Patrick Connolly, Michael Grady, Irish laborers, ages unknown, died within the same 2-week period in May 1870. The newspaper accounts mention them collectively, not individually. 3 more caisson workers succumbed to the mysterious affliction. Jaminet's medical reports provide more detail. Riley experienced sudden blindness followed by convulsions. Connolly was found unconscious in his boarding house, never regained consciousness. Grady's symptoms appeared mild initially: joint pain, fatigue, then rapidly progressed to paralysis and death. The pattern was consistent but unpredictable. Some men worked in the caissons for months without serious symptoms. Others fell ill after a single shift. Some men experienced joint pain that resolved after rest. Others suffered paralysis, blindness, or death. Dr. Jaminet tried to identify risk factors: time spent at depth, speed of ascent, individual constitution, alcohol consumption, pre-existing health conditions. He found correlations but no definitive causal pattern. His recommendations evolved as he gathered data. Initially, limit shift length to 2 hours. Later, implement staged decompression. Pause in the airlock. Allow pressure to decrease gradually rather than immediately. Later still, restrict men who show mild symptoms from returning to depth until fully recovered. Some recommendations were adopted, others were considered too disruptive to construction schedules. The caisson workers knew the risks. Word spread through the boarding houses where laborers lived. Men were dying or becoming crippled. Some workers quit. Others demanded higher wages, which they received. Caisson work paid approximately 30% more than surface construction work. Some men stayed because they needed the money. Some stayed because they'd invested time learning the work and didn't want to start over at lower wages elsewhere. There was no workers' compensation system. An injured or killed worker received wages only for time actually worked. Medical expenses were the worker's responsibility. If a man died, his family received nothing unless they could prove the employer was negligent, which required hiring a lawyer, which required money most families didn't have. The bridge company's position, never explicitly stated but evident in their actions, was that caisson work was voluntary and the risks were known. Men who accepted higher wages accepted higher risks. This was consistent with 19th century labor law and prevailing attitudes about industrial accidents. The legal concept of assumption of risk meant that workers who knowingly took dangerous jobs couldn't sue for compensation when the known dangers materialized. Some workers didn't understand the risks because they couldn't read the English-language newspaper accounts describing caisson disease. Many caisson workers were recent immigrants, Irish, German, Italian, with limited English proficiency. They understood dangerous work, higher pay, but not necessarily the specific medical mechanisms or mortality rates. The work itself was straightforward. Enter the caisson through the airlock, descend to the chamber floor, shovel mud and sand into the pump intake, exit through the airlock when your shift ends. The difficulty was entirely physiological, invisible until symptoms appeared. Unlike construction work where you could see the hazard, falling from scaffolding, being struck by material, caisson disease operated through mechanisms the workers couldn't observe and the supervising physicians didn't fully understand. 14 or 15 deaths total depending on which sources you trust. Some accounts say 14, citing Jamine's report. Other accounts say 15, citing later summaries that included one additional death not in Jamine's original documentation. 2 workers permanently paralyzed, unable to work again. 77 severely afflicted but survived. 119 total cases documented. The undocumented cases, men who experienced mild symptoms and didn't report them, men who left the job site before symptoms appeared and never returned, men who died of other causes but whose deaths might have been hastened by vascular damage from decompression sickness. The medical understanding in 1870 was insufficient to diagnose all cases, especially delayed or chronic effects. The Brooklyn Bridge, built simultaneously in New York, experienced similar casualties. Over 100 documented cases of caisson disease, including 3 deaths. The Brooklyn Bridge caissons went to 78 feet on the Brooklyn side, 45 feet on the Manhattan side. The Eads Bridge caissons went to 78 feet on the East Pier, 123 feet on the West Pier. Greater depth meant higher pressure, which meant higher risk. Washington Roebling, chief engineer of the Brooklyn Bridge, suffered severe decompression sickness himself. He survived but was partially paralyzed and never fully recovered. He supervised the bridge's completion from his apartment, watching through a telescope while his wife, Emily Warren Roebling, relayed his instructions to the construction crew. This was considered notable because the chief engineer survived and continued working despite disability. James Eads did not work in the caissons. He designed them, supervised their operation, made decisions about depth and pressure requirements. He experienced the stress of the project, nervous exhaustion, health problems that required extended leave in Europe, but not the physical risks that killed and disabled caisson workers. The distinction between engineering risk and labor risk was absolute. Eads risked his reputation, his financial investment, his health from overwork. The caisson workers risked their lives daily. Both risks were real, but only one resulted in bodies. The project's narrative focuses on Eads, the self-taught engineer, the visionary, the man who built the impossible bridge. The workers appear as casualties in medical reports, names in newspapers, statistics in historical summaries. 15 dead, 2 disabled, 77 severely afflicted. The numbers are preserved. The individual stories, what those men thought about the work, what their families experienced, how their communities responded, mostly are not. Dr. Jamine's reports were published and circulated to the medical community. His observations contributed to the eventual understanding of decompression sickness and the development of safer caisson construction practices. Later bridges, the Brooklyn Bridge, the Fourth Bridge in Scotland, the bridges that followed, benefited from the knowledge gained at the Eads Bridge. The workers who died contributed to that knowledge involuntarily by serving as data points in Jamine's study. This is standard practice in industrial progress. Early adopters of dangerous techniques suffer casualties. Later practitioners implement safety measures developed through studying those casualties. The first caisson workers didn't know they were contributing to medical knowledge. They knew they were digging in mud under pressure for higher wages. Some survived. Some didn't. The bridge was completed using knowledge derived from their deaths. The bodies are somewhere. 15 men buried in St. Louis cemeteries, presumably, though the specific graves are not documented in any centralized record. Some families might have transported remains back to Ireland or Germany for burial. Some men might have been buried in potter's fields if no one claimed the body or paid for burial. The records are incomplete. The bridge remains. Steel and stone, maintained and repainted, carrying Metrolink trains and automobiles. The caisson chambers where men died are sealed under limestone piers, inaccessible, filled with the sand and mud they excavated. The work they did persists. Their names mostly do not. James Moran died March 19, 1870. The East Pier was completed 11 months later. The bridge was finished 4 years after that. The bridge is named for Eads, not for Moran or Myers or Riley or any of the others who died building it. This is how infrastructure commemorates its costs. It doesn't. The Eads Bridge carries approximately 8,100 vehicles per day as of 2014. This number dropped from 11,100 after the Stan Musial Veterans Memorial Bridge opened in February 2014, providing an alternative Mississippi River crossing. 3,000 vehicles per day migrated to the newer bridge, which has higher clearance, smoother approaches, and more direct connections to interstate highways. 8,100 vehicles is not insignificant. It's approximately 3 million vehicles per year. Each vehicle represents a decision: this bridge, this route, this crossing point. Some drivers choose the Eads Bridge for convenience. It connects directly to downtown St. Louis and the Gateway Arch grounds. Some choose it for symbolism, crossing the historic bridge, the oldest on the Mississippi. Some choose it because their route requires it. Most don't think about the choice at all. 300 Metrolink trains cross the bridge daily. Each train carries dozens to hundreds of passengers, depending on time of day and direction. Eastbound morning rush, workers commuting from Missouri to Illinois. Westbound evening rush, reverse flow. Weekend and off-peak, tourists, students, residents making trips that don't follow commuter patterns. The bridge is the only Metrolink connection between Missouri and Illinois. If the bridge closes, the light rail system is severed. This makes the bridge essential in ways that are invisible until disrupted. During the 2012 to 2016 rehabilitation, Metrolink service continued on a single track. Trains shared that track, alternating directions, with reduced frequency during peak work periods. Passengers experienced delays. Some shifted to driving or other routes. The system functioned barely because the bridge remained partially operational. A complete bridge closure would require either bus bridges, Metrolink passengers transferred to buses that cross at another location, or service suspension. Both options are economically and operationally problematic. Bus bridges require coordination with road traffic, additional vehicles and drivers, passenger inconvenience that reduces ridership. Service suspension severs the transit network and strands passengers on both sides of the river. So the bridge must remain operational. This necessity drives the maintenance imperative described in the previous chapter. You maintain the bridge not because you want to, but because the alternative is unacceptable. The $48 million rehabilitation was not discretionary. It was required to keep the structure functional for the transit system and vehicular traffic that depend on it. The bridge's current function bears little resemblance to its designed function. It was built for railroad freight, heavy trains carrying manufactured goods, raw materials, agricultural products across the Mississippi. The railroad deck now carries light rail passenger trains. The upper deck, designed for wagons and foot traffic, now carries automobiles and pedestrians. The tunnel, designed for freight locomotives, now carries Metrolink trains powered by overhead electric wires. This functional transformation is why the bridge survives. Structures that cannot adapt to changing uses get demolished. The Brooklyn Bridge adapted from horse-drawn carriages to automobiles to modern traffic. The Eads Bridge adapted from freight railroads to light rail. Adaptation requires investment, modification, sometimes radical reimagining of how the structure serves the city. The reimagining began in the 1980s. By that point, the bridge's railroad function was obsolete. The Terminal Railroad Association had shifted freight traffic to other bridges. The Eads Bridge was underutilized, deteriorating, closed to automobile traffic due to safety concerns. It was a historic landmark but not a functional piece of infrastructure. The Bi-State Development Agency proposed using the bridge for a new light rail system, Metrolink, connecting St. Louis and East St. Louis. This required negotiations with the TRRA, which owned the bridge, and the City of St. Louis, which owned the upper deck. The eventual arrangement, TRRA traded the bridge to Bi-State and the city in exchange for the MacArthur Bridge. Bi-State took ownership of the superstructure and lower deck. The city retained the upper deck. Conversion work began in 1989. The lower deck was completely rebuilt for light rail. New tracks, new electrical systems, new safety features. The upper deck was rehabilitated for automobile and pedestrian traffic, which had been suspended since 1991 due to structural concerns. A Metrolink station was built inside the West Approach Tunnel, utilizing space that had been closed after the original Main Street station was eliminated. The conversion cost was substantial. Exact figures are difficult to isolate because the work was part of the larger Metrolink system construction. But the investment preserved the bridge by giving it a new function. Without the light rail conversion, the bridge likely would have continued deteriorating until demolition became the only economically rational option. Metrolink service across the bridge began in 1993. The upper deck reopened to automobile traffic in 2003. By 2012, when the comprehensive rehabilitation began, the bridge had been functioning in its new role for nearly 2 decades. The rehabilitation extended that function for another 50 to 75 years. This raises the question, what happens in 2091? The bridge will be 217 years old. The steel will have been in service for over 2 centuries. Maintenance costs will have compounded. Technology will have changed in ways we can't predict. Will the bridge still serve a necessary function? Will the political and fiscal systems necessary to fund another rehabilitation still exist? These are not hypothetical questions for a structure expected to last until 2091. They're planning considerations that should inform decisions made now. But infrastructure planning rarely extends beyond 20 to 30 years because predicting longer-term needs is essentially speculation. The bridge's survival so far has depended on a series of coincidences: bankruptcy that transferred ownership, monopoly control that provided maintenance funding, antitrust action that prevented abandonment, public transit needs that created a new function, federal stimulus money that funded rehabilitation. None of these were guaranteed. Each could have gone differently, resulting in a demolished bridge and a gap in St. Louis's infrastructure history. This is the fragility beneath infrastructure's apparent permanence. The bridge seems permanent because it's steel and stone, because it's massive, because it's been there for 150 years. But its existence depends on continuous human decisions to maintain it, fund it, use it, adapt it. Those decisions are contingent on economic conditions, political priorities, institutional capacity, and technological needs that shift over time. James Eads believed he was building permanent infrastructure. He calculated the loads, specified the materials, overbuilt the structure to ensure longevity. What he couldn't calculate: bankruptcy, monopoly, antitrust, technological obsolescence, functional transformation, rehabilitation costs exceeding original construction costs when adjusted for inflation. He built a bridge that could physically last centuries. Whether it actually lasts depends on factors outside engineering. The river doesn't care. The Mississippi flows at approximately 1.2 million gallons per second at St. Louis during normal conditions, 3 million gallons per second during flood stage. The bridge obstructs this flow marginally. 3 piers in the water create turbulence, slightly raise water levels upstream, alter sediment patterns, but the river adapts around the obstruction. It erodes banks elsewhere, deposits sediment downstream, continues flowing. From the river's perspective, measured in geological time, the bridge is temporary. 150 years is nothing. The river has flowed for thousands of years before the bridge, and will flow for thousands of years after. Whether the bridge stands until 29-1 or fails next decade, the river continues. This should be humbling for anyone involved in maintaining the structure, but humility doesn't appear in engineering specifications. The bridge remains for now. 8,100 vehicles daily, 300 trains daily, thousands of pedestrians annually walking across for the view or the history, or because it's there. The structure serves the city because the city has invested in preserving it. When that investment stops, whether in 2091 or sooner, the structure will stop serving. The question isn't if, but when, and whether anyone will care enough to decide it matters.